So I'm going to do a couple examples here of using the ratio test. Now, in general, what would lead me to think of trying the ratio test here is the exponential piece and the factorial. One or both of those are usually decent signs that we might want to try the ratio test. So the ratio test, we do the limit as n goes to infinity of the absolute value of a sub n plus 1 over absolute value of a sub n. Now a sub n plus 1 is our sequence here with n plus 1's in for the n's. So 2 to the n plus 1, all in the exponent there, times n plus 1 factorial. Now what I do to save time, instead of dividing by a sub n, I multiply by the reciprocal. So I'm going to multiply by 2 to the n factorial over 1. We're going to do the limit as n goes to infinity. And it's the absolute value of this. As you can see, everything's going to be positive. Okay, so by rewriting, I'm going to see some cancels in here. So limit as n goes to infinity. On top, I'm going to leave it as 2 to the n times n factorial. Now, 2 to the n plus 1. I can split that up. I can rewrite that as 2 to the n times 2 to the 1. Or 2 times 2 to the n. That's the same thing. n plus 1 factorial, I can rewrite as n factorial times n plus 1. So, now we see our cancels. The n factorials cancel, 2 to the n and 2 to the n cancel. I basically get left with the limit as n goes to infinity of 1 over 2 times n plus 1. We have something where the denominator is going to get really large, the numerator is not going to grow at all. That equals 0, which is less than 1. So our original series converges by the ratio test. And it's a really good habit to credit which test you're using when you're done. Okay, let's do one more while we're here. Something with a little bit of work to it. This one's an interesting one. So we have n plus 1 factorial over n plus 1 to the n. So right off the bat, we can see the ratio test in this. We see the exponential piece. We see the factorial piece. So we're going to do the limit as n goes to infinity of now when I put in n plus 1's for all these, I'm going to end up with n plus 2 factorial over n plus 2 to the n plus 1 times 1 over a sub n, or the reciprocal of this, n plus 1 to the n over n plus 1 factorial. This one, again, is going to be a little bit of work here, so let's see what we can figure out. Some stuff will work out nice, some may not. Okay, so let's see what we can rewrite in this guy. Well, I know that I can rewrite n plus 2 factorial as n plus 1 factorial times n plus 2. And what else do we know? We have this. I can actually rewrite this underneath here. I can pull out one of the n plus 2's basically. I'm going to write it as n plus 2 times n plus 2 to the n. So that one extra n plus 2 I'm splitting off. Times n plus 1 to the n over n plus 1 factorial. Limit as n goes to infinity. Definitely some nice cancels here. Gone. The n plus 2's will cancel. Here's where it's going to get a little bit interesting. We have the limit as n goes to infinity of n plus 1 to the n over n plus 2 to the n, which I can write those both to the same n. limit as n goes to infinity of n plus 1 over n plus 2 all to the n. I have, if we try and do the limit, I've got a 1 to the infinity case. This is a L'Hopital's. It's indeterminate. Now what we're going to do though is we're going to do it using logarithms, because I need to rearrange this stuff just a little bit, so let me get myself some more room. So I'm going to do the limit and then we'll come back to this and see what we have. So we're trying to we're basically saying we're looking for the limit L, which is the limit as n goes to infinity of n plus 2 over n plus 1. Make sure I got that the right direction. I do not. N plus 1 over n plus 2 to the n. So what I'm going to do is I'm going to do a natural log on both sides. Now I can pull the limit out of the natural log, and it's essentially the right hand side I want to concentrate on. Because what happens now is I'm taking the limit as n goes to infinity, and this allows me to pull the n out in front. N times ln n plus 1 over n plus 2. So now I have an infinity times 0 case. I need to write it as infinity over infinity or 0 over 0. Easiest probably is going to be to rewrite this as a 0 over 0, because I think it's going to make our lives easier when we go to do our derivative. So I've got limit as n goes to infinity of n, so I'm going to rewrite this as ln of n plus 1 over n plus 2 over 1 over n. Same exact thing, but now I've got an infinity, sorry, not infinity over infinity, a 0 over 0 case. Now we'll be able to apply L'Hopital's rule, but before I do, I want to make this thing a little easier to deal with. I'm going to use a property of logs here. So if the limit as n goes to infinity, I'm going to rewrite that as ln of n plus 1 minus ln of n plus 2. Save us some time on the derivative. 1 over n. Now I'm going to apply L'Hopital's. I like to put an h there to remind myself that's what I did. So I've got the limit as n goes to infinity. On top, I'm going to have 1 over n plus 1 minus 1 over n plus 2. Very nice. On bottom, I am going to have, let's see, we have an n to the negative 1, so it's going to be negative 1 over n squared. Okay. So, let's see, what can we do? Well, maybe I decide to simplify that numerator first. So as a common denominator on top, so I have the limit as n goes to infinity of n plus 2 minus n plus 1 over n plus 1 times n plus 2 all over negative 1 over n squared. So if you're not sure what I did there, I found the common denominator between these two, which is n plus 1 times n plus 2. This one will become n plus 2 over the common denominator, this one will become n plus 1, and that's where that numerator came from. What's neat about this, the n, positive n and negative n cancel. 2 minus 1, we're going to get 1. And now I'm going to flip this and multiply. So when all's said and done, kind of combining some steps just to, because I know this video is getting a little long, this simplifies down to just a positive 1. And I'm going to flip the denominator and multiply. So n squared times 1, so I get a negative n squared over n plus 1 times n plus 2. That negative is actually quite important. So when I take this limit, I'm not going to use L'Hopital's again, but hopefully you're you're seeing it. I've got an n squared over an n squared. They're going to grow at about the same rate. So it's going to go to negative 1. Now my limit is not negative 1. Remember, back up here, ln of L is negative 1. So I know that the natural log of my limit is negative 1, so my limit is e to the minus 1. It's right there where you can see it, because that's greater than 0. But it's less than 1. So I come back to here. This is equal to e to the negative 1, or 1 over e, which is less than 1. So our series is in fact convergent by the ratio test. And we are done.